Hi, I'm Bjorn Turius, and this is part 6 of my video series on process control. In previous videos, we have seen how a simple feedback controller can reduce disturbances to the process. We also found that the controller is the most effective when the gain is high. Unfortunately, there appears to be a limit to the magnitude of the controller gain that the loop can actually tolerate before it starts self-oscillating. Why is that? Of course, I knew the answer conceptually and mathematically, but I have struggled with finding a way of visualizing it in a simulation. Take our heated tank, for example. When a disturbance enters the tank, it has a certain effect on the tank temperature. The controller sees this as its PV and acts to compensate. The moment the controller compensates, the tank temperature is now a mixture of the original disturbance and the controller's action. When the composite signal eventually starts self-oscillating, it's really hard to see why. A couple of years ago, I came up with an idea of how to keep the signals apart and clearly see what's going on. This idea is implemented in the Control Concepts app and involves using 2 tanks instead of just one and altering the signal diagram slightly. The alternate PNID is available by pressing the Open Loop PNID button above the strip charts. Please note that the regular PNID is found in the little book icon. The Open Loop PNID looks like this. In this arrangement, the tank TC is sending its output signal to the heater of the second tank. We get that effect by activating the open loop signal propagation switch on the config panel as shown in this figure. Now when we have a disturbance entering the top tank, it does not get compensated in that tank by the controller. Instead, the controller sends its signal to the second tank, and its temperature starts changing in tune or in rhythm with the disturbance. What's the point of that? The point is that the response in the second tank is what the controller would have done to the disturbance without being mixed with its own response. Let me show you how that works in the simulator. I'm starting out the simulation with a sine wave disturbance of 0.5 periods per hour and an amplitude of 20 degrees. The dead time is 0.1 hours and the open loop signal propagation is on. The tank temperature controller's gain is 8, but the system is not driven into self-oscillation because the top tank is not under feedback control. Instead, the bottom temperature is varying in harmony with the top tank due to the controller action. The red curve, being the bottom tank temperature, is almost perfectly offset against the top temperature, which is the blue curve, and there would be good cancellation under feedback control. Let's now increase the period to 1 frequency to 1 period per hour. As we have seen before, there is more attenuation of the temperatures in both tanks with higher frequency. However, most importantly, the red curve is now further shifted to the right. This is a combination of the tank leg, but also of the exchange column, the dead time, before the second tank. I'm now going to increase the frequency even more to 2 periods per hour. Attenuation is even more pronounced, but so is phase shift. It's mostly the dead time element that keeps contributing phase shift, since the first order lag only contributes at the most 90 degrees. Finally, we set the disturbance frequency to 2.5 periods per hour. We have previously found this to be the natural frequency of the system under feedback control. It is evident that the bottom tank temperature has shifted over completely to be aligned with the top tank temperature at a gain of 8. Their amplitudes are also the same. This is why self-oscillation happens. If we stay at this frequency but lower the gain to say 5, where we know that this system is stable, let's see how it shows up in the simulation. You see the phase shift is the same, but the amplitude is different. the red curve doesn't quite come up to the blue curve, and self-oscillation would not occur. Let's try something that's even greater than 8. Phase shift is still the same, but the amplitude of the red curve is clearly greater than the blue curve, and the system would be driven totally unstable under these conditions. I will now try to interpret these results in a Bode diagram. These Bode plots have been prepared for a system with the parameters in blue. They are the first order lag with dead time representation of the process system we just simulated. First, a reminder of what are we looking at. The top curve is the log modulus plot. It's 20 times the 10 logarithm of the product between the process gain and the controller gain, adjusted for the attenuation caused by a first order lag. The bottom graph is the sum of the phase shifts of a first order lag and a dead time element versus frequency. Recall that a first order lag has a phase shift of maximally minus 90 degrees, and that the shift is minus 45 degrees at 1 over the time constant. That point is shown as a green circle at 5 radians per hour. The dead time element loses phase angle indefinitely. The point where it lost minus 180 degrees is shown as a small pink circle in the phase angle diagram. We found in the simulation that the ultimate frequency of our system occurs at 2.5 periods per hour, or 15.7 radians per hour. That line is indicated in orange in the plots. At that frequency, the log modulus is 0, and the phase angle is minus 180 degrees. Does that make sense? Yes, because the subtraction of the measurement from the set point in a feedback loop creates minus 180 degrees phase shift right away when it becomes the mirror image of the process value. That's how we would like to keep it for all frequencies for optimal disturbance cancellation. Unfortunately, process dynamics shifts the response signal further and further to the right. We can read off the phase shift and log modulus for the frequency we tested, as indicated by the small triangles in the plots. When we get close to 2.5 periods per hour, the phase shift is close to minus 180 degrees. At 2.5 periods per hour, the phase shift is exactly 180 degrees, and the output signal is aligned with its measurement. If at that point the loop gain is equal to 1, the signals overlap completely, and we get self-oscillation. A loop gain of 1 has a log modulus of 0. Bode diagrams are one of the classic tools for control system analysis and design. While they have increasingly had to give way for direct dynamic simulations, they're still excellent tools to anticipate and predict what a control loop will do based on open loop information alone. In this video, I hope to have shown why too much gain in a control loop can cause self-oscillation and instability. The dynamic simulation to do so was arranged in an open loop fashion using 2 tanks. The simulated response of tank 2's temperature from a controller acting on a disturbance in tank 1 is nicely reflected by the open loop Bode plot of the system.